path that redshift 6 might imply about reionization.
Right. All right. Hi, everyone. My name is Chris. I'm a third-year graduate student at UC Riverside, and I'm going to talk about the implications of a short mean-free path at redshift 6 for reionization. The mean-free path is just the typical distance that an ionizing photon travels through the IgM before it's absorbed. And this is set by the opacity of the ionized gas in the IgM, as well as the distribution of the neutral gas. And in this figure, I've shown the red lines indicate possible paths that an ionizing photon could take during reionization. And as you can see, the mean-free path evolves very quickly during and after reionization. So the direct measurements of the mean-free path are a powerful probe of the reionization era. Now, recent work has pointed towards reionization finishing at redshift 6 or possibly even later. And these works have invoked late reionization to explain the large opacity fluctuations in the Lyman alpha forest that are observed below redshift 6. And so measurements of the mean-free path can also distinguish between these models because you expect different mean-free paths depending on how much neutral gas there is in the IgM. Now, until recently, measurements of the mean-free path at redshifts less than 5.2, which I've shown here from Warsack et al. 2014, have been consistent with existing reionization models. On this plot, I've shown two models of the mean-free path predicted by two theoretical models of reionization, one from Keating et al. 2020, in which reionization ends late at redshift 5.3, and one from Diagnostic et al. 2020, in which reionization ends at redshift 6. And as you can see, both models are consistent with the existing measurements. Now, the new measurements recently new measurements were published of the mean-free path from Becker et al. 2021, and these measurements changed the story a little bit. So their measurement at redshift 5.1 is consistent with existing measurements and theoretical predictions, but the measurement at redshift 6, which I've highlighted here, is significantly shorter than predicted by a model of reionization that is 20% neutral at redshift 6. So this presents a challenge for existing reionization models, and it's a challenge that we'll be addressing in this talk. Now, work has also been done to understand the impact of the ionized IgM on the mean-free path. Recently, Park et al. 2016 and Diagnostic et al. 2020 ran very high-resolution simulations of the response of the IgM to the ionized IgM to reionization, and they found a rather complicated picture. So as I've shown in this figure, the IgM evolves from a highly clumpy state with a high recombination rate with a very high recombination rate just after ionization. And over a time scale of a couple 100 million years, the IgM goes to a much more diffuse state with a lower recombination rate. And this process is driven by photoheating from reionization, and takes place again. It takes place over a time scale of a couple 100 million years, which is comparable to the time scale of reionization. So modeling these processes is also important for capturing the mean-free path accurately. So to model reionization on large scales, we developed a new ray tracing radiative transfer code and post-process static density fields with ionizing radiation from halos with masses greater than 10 to the 9 solar masses. This figure shows light cone slices through the density and ionization fields on top, and the photoionization rate fields on bottom from one of our simulations. And for each of these simulations, we set the global ionizing emissivity of our sources by hand at each redshift to obtain the desired reionization history. And we've also developed a subgrid model for the impact of the ionizing photon sinks, the gas structures that set the recombination rate, that are present on very small scales. We use a suite of hydro-RT simulations with very high spatial resolution, like those from DLOECU et al. 2020, to capture the evolution of the ionizing photon opacity in environments with different photoionization rates, redshifts of reionization, and large-scale overdensities. And what I've shown in this plot is that each 1 megaparsec over H cell in our large volume reionization simulation, pictured on the left, is effectively modeled by a simulation with kiloparsec scale resolution, spatial resolution, which is pictured on the right. And in doing this, we achieve a formal dynamic range of over 5 orders of magnitude in spatial scale, while resolving all of the physics that's most important for setting the mean free path in ionized gas. Now on to our results. The first comparison we considered are 2 models of reionization, one in which reionization proceeds rapidly in its latter half with a midpoint of redshift 5.1, and our gradual model, which has a midpoint of redshift 8.5 and proceeds more gradually in the latter half. Note that both models end reionization around redshift 5.1, so both of these are late reionization models. The left panel shows the ionization history for both models alongside constraints from the literature, and the right panel shows the emissivity history. Now, our main conclusion here is that the rapid model does a better job of reproducing the quick evolution in the photoionization rate, which I've shown on the left, and the mean free path, which I've shown on the right here. Notice that while the gradual model can reproduce the low redshift evolution of the mean free path very well, it misses the rapid evolution from z equals 6 towards lower redshifts, and also undershoots the low redshift measurements of the photoionization rate by a factor of a few. The rapid model agrees reasonably well with photoionization rate measurements and captures the quick evolution in the mean free path. And another comparison we considered is whether reionization is driven by faint or bright sources. The main difference between these models is that in the model that's driven by fainter sources, the sources are less clustered in space. They are less biased with respect to the underlying density field than in the bright sources model. Note that both of these models have identical emissivity histories and almost exactly the same global ionization history. So I'm shown here. Our conclusion from this comparison is that reionization by faint galaxies reduces the mean free path at all redshifts compared to reionization by bright sources, particularly at redshift 6. This is for 2 reasons. One is that the less clustered sources result in smaller photoionization rates on average, which you can see on in the left panel here. And at redshift 6, when there's a significant amount of neutral gas in the IGM, the typical ionized bubble size is also smaller in the faint sources model. And this further reduces the mean free path at redshift 6. Now, the last question we considered is whether the quick drop in emissivity in our rapid model, which you can see in the black curve here on the right panel, is necessary to keep the photoionization rate and mean free path from outpacing the measurements at low redshift. So what we did here was we allowed the emissivity to go flat after redshift 6.5, and we added additional sinks to our model by changing the opacity in our subgrid model until we were able to fit the evolution of the mean free path measurements at low redshift. And we refer to this as our enhanced sinks model, which is shown here by the red curve. Our main conclusion here is that missing sinks, adding additional sinks to our model can indeed regulate the photoionization rate and mean free path at the lowest redshifts. Notice that the mean free path here on the right is in good agreement at all redshifts, with all the measurements at all redshifts. And the photoionization rate measurements also agree well with the theory. So to put some numbers to this, to get good agreement with the mean free path, we had to increase the opacity in overdense gas in our model by a factor of 1.3 and 2 at redshift 6 and 5.2 respectively. We also looked at the ionizing efficiency and escape fractions in our models. For our rapid models, for reasonable values of the ionizing efficiency, we found that our rapid models are consistent with escape fractions of 10 to 30% at redshifts greater than 6. And this is consistent with previous work that has found that higher escape fractions are needed at these redshifts than what we see at lower redshifts in order to supply the photons needed to complete reionization. To put some additional numbers to this, the typical UV magnitude of the sources that drive reionization in our rapid model is negative 12.9 and negative 14 at redshift 6 and 8, respectively. Our last result is the photon budget required to complete reionization. In this plot, I've shown the number of photons per H atom, cumulative number of absorptions per H atom in each of our models, with reionization again ending at redshift 5.1. We find that all of our models require about 3 photons per H atom to complete reionization, which is a factor of 1.5 to 2 more than has been found in many previous works. However, one caveat to all of our models is that the mean free path we predict intersects the upper 1 sigma error bar of the Becker et al. 21 measurement at redshift 6 and has a neutral fraction of about 20%. Now, the recent work of Davies et al. 2021 found that if the central mean free path measurement the central mean free path measurement at redshift 6 and existing dark pixel constraints are both assumed, the number of photons required to complete reionization increases by a factor of 2, which would put even more stringent demands on high redshift sources. I'll leave a conclusion slide here. Thank you very much. Are there any questions?
Thank you, Chris. Looks like we have a couple of questions already. If you wanted to wait maybe a little bit more, Steve.
Sure, yeah, we'll wait 10 seconds or so, and then I'll ask the first question. So the first question is about the measurements. They want to know how are measurements of the mean free path made, and then ask about why the measurement at redshift 6 has a large error and whether that's due to cosmic variance.
So very good question. So the mean free path is measured using QSO absorption spectra by fitting the opacity or fitting the flux profile to an opacity law. And part of the reason for the large error bars at redshift 6 is that the measurement is very hard to make, in part because the mean free path at that redshift is so short that there's a quasar proximity zone effect that you have to account for, and so part of the error comes from correcting for that effect.
Okay, kind of a related question is, a key ingredient of the short mean free path measurement is the proximity effect on scales larger than the mean free path. Do you think that accounting for effects like the finite lifetime of QSOs and or clustering around QSOs could counteract the proximity and increase the measurement of the mean free path length?
That's also a really good question. I'll have to get back to you on that. I haven't looked at that in too much detail, but that's a very good question, and I will definitely get back to that.
That's good. Another question, does your recombination term explicitly include the clumping factor? If not, then that would naturally provide the sync boosting.
Yes, so the way we implement our subgrid model is by directly modeling the mean free path in the small scale simulations, which implicitly includes the clumping factor.
Great. Yeah, there are a few other questions that you can address by Slack, but in the interest of time, we should move on now. Thank you very much again, Chris. Okay, so next up is Zheng Yu Jin, and she'll be telling us about new model independent constraints on the NGM neutral fraction.
Hello, everyone. I'm Xiaoyu. I'm a first-year grad student at University of Arizona, and thanks for this amazing chance to present our work at SAZERAC conference. Today, I'm going to talk about our recent work that uses high-range quasar to derive model-independent constraint on the IgM neutral hydrogen fraction up to range 6.8. My collaborators on this project are Professor Xiaohui Fan, Dr. Qin Yang, and Dr. Fei Wang. Before I talk about our measurement, I want to give a very brief view about reionization. Reionization is an important landmark in the evolution of integrated medium. So it's very crucial to investigate how the neutral hydrogen fraction is evolving during this epochal reionization. The neutral hydrogen fraction can be measured from high-redshift galaxy or high-redshift quasar. But through this high neutral hydrogen fraction measurement from high-redshift quasar, which is shown by the figure here, you can find there is a very clear gap in the measurement at around redshift 6.5. Thus, therefore, in our study, we want to use high redshift quasar to constrain the neutral hydrogen fraction in this redshift range. There are several commonly used methods to probe this neutral hydrogen fraction with high redshift quasars. For example, we can study the transmission spike in lemma alpha and lemma beta forest to measure neutral hydrogen fraction. The neutral hydrogen fraction can also be measured from the mean free path of ionizing photons. From individual quasars, the neutral hydrogen fraction can be measured from the damping ring feature in the spectrum. The size of quasar proximity zones can be also used to measure the neutral hydrogen fraction. But all of those four methods I just mentioned, they are more or less model dependent, whether on the IgM model or quasar intrinsic spectrum or quasar lifetime. The only model-independent constraint from high-range quasar is studying the dark pixels in lemma alpha and lemma beta forest. This is the method we are using in our study. This method about use dark pixel in lemma alpha and lemma beta forest was first used by Magritte 2011. The basic idea is that they beam the spectra in lemma alpha and lemma beta forest on a larger pixel scale to get a higher limiting optical depth. So those beam spectra are shown by those vertical bars here in this figure. For the highly ionized region, they will appear as very bright pixels in this figure. But for the region that are not very highly ionized, they can attenuate the flux emitted by the quasar to a very low level. Thus, they will appear as dark pixels in this figure. We can adopt criterion to identify those dark pixels. For example, here, Magritte used a 2 sigma noise level, which is shown by this red solid line to identify dark pixel. If a pixel has a flux smaller than 2 sigma noise, it will be identified as a dark pixel and plotted in black in this figure. The current fraction of this dark pixel will be corresponding upper limit on neutral hydrogen fraction. And this constraint doesn't depend on any model assumptions, such as the model of a reionization model or quasar intrinsic spectral shape. Thus, we are using this in our study. So we set 53 high-redshift quasar. Their redshift range is about 5.73 to redshift 7.085. Here is a redshift distribution of those quasars. We have spectra from BLT, CAC, MMT, Magellan, LBT, and Gemini. For the wavelength range of lemma alpha forest, we are using this wavelength range in the rest frame in our study. The shorter wavelength cut is to exclude oxygen 6 emission in the quasar intrinsic spectrum, and the longer wavelength cut is to avoid contamination from quasar proximity zone. For the lemma beta forest, we are using this wavelength range in our study. The shorter wavelength cut is to exclude lemma gamma emission and lemma gamma forest. The longer wavelength cut is to match to the same absorber redshift as the longer wavelength cut of lemma alpha forest. Then we follow the method in Magritte 2011 to beam the spectrum and use this 2 sigma noise level to identify the dark pixels in our spectrum. We calculate the fraction of dark pixels from individual quasars and derive their average value in each redshift beam. And we use Diagnostic to calculate their 1 sigma scatter. Here, when we calculate the dark pixel fraction, we exclude pixel with a limiting optical depth smaller than 2.5. The limiting optical depth in our study is only used to indicate the quality of pixel to probe the neutral hydrogen. If a pixel has a higher limiting optical depth, this means it has a higher ability to probe the neutral hydrogen. And here is our measurement. The constraint from lemma alpha force are shown by those blue upper limits, and constraint from lemma beta force are shown by those red upper limits. Apart from these two constraints, we also get a combining constraint from lemma alpha and lemma beta force, and those are shown by those magenta upper limits. In this constraint, a pixel is dark only if it's below 2 sigma noise, both in lemma alpha and lemma beta force. And this combining constraint from lemma alpha and lemma beta force give us the tightest constraint on the neutral hydrogen fraction. From this combining constraint, it puts an upper limit on neutral hydrogen fraction about 35% at redshift 5.5. And this upper limits increase to about 80% at redshift 6.3, also at redshift 6.5. Later, this upper limit on neutral hydrogen fraction increased to about 95% at redshift 6.7. And those measurements are the first constraint from dark pixel study in those redshift range. Later, we use a higher limiting optical depth cut to select pixel with very high ability to probe the neutral hydrogen. And the result plotted with pixel with high limiting optical depth cut at 4.5 is shown on right-hand side. And as a comparison here, I also present this plot I show on the last slide. This is plot with a smaller limiting optical depth cut on pixel with at 2.5. And on each figure, the number of pixels used to calculate this dark pixel fraction is shown on the upper panel. With this high limiting optical depth cut at 4.5, we can find it dramatically reduced the number of pixels used to calculate dark pixel fraction. Because at high redshift end, because the sky is very noisy at high redshift end, so we don't have many pixels with high limiting optical depth to calculate the dark pixel fraction. Thus, with a high limiting optical depth cut at 4.5, we can no longer put a valid constraint on the neutral hydrogen fraction, except for one. But with this high limiting optical depth cut, it can make the constraint at lower redshift end tighter. So compare with the upper limits here, you can find the upper limits with a higher limiting optical depth cut looks lower. Furthermore, we present more constraint on the neutral hydrogen fraction from other high redshift quasar study. The measurements on neutral hydrogen fraction from effective optical depth in lemma alpha forest are shown by these black squares and green squares. They put a lower limit about on neutral hydrogen fraction about 10 to -4 at redshift 6. At higher redshift range, there are some individual measurement on neutral hydrogen fraction from the quasar damping wings. They are shown by those hexagons here. And from those measurements from quasar damping wings, you can find they are pretty diverse in the measured neutral hydrogen fraction. The reionization history derived from Planck is shown here. The 1 sigma confidence interval is shown by this dark gray shaded region. And the 2 sigma confidence interval is shown by this light gray shaded region. Represent our upper limit on neutral hydrogen fraction at low redshift end by those magenta upper limits. Because here we want to get a tighter constraint on the neutral hydrogen fraction with a higher limiting of the depth cut at 4.5 to get a tighter upper limits. And as a comparison here, we also include the result from McGrew 2015 by those blue upper limits. They also use dark pixel to put upper limit on neutral hydrogen fraction in this redshift range. And our results are consistent with their measurements. At higher redshift range, because the sky is very noisy, so here we use a smaller limiting optical depth cut at 2.5 to derive this upper limit on neutral hydrogen fraction. And our results are constrained about 80% on the neutral hydrogen fraction at redshift 6.3 at 6.5. And this upper limit on neutral hydrogen fraction increased to about 95% at redshift 6.7. And overall, our upper limit on neutral hydrogen fraction increased very fast with redshift. And this might indicate that the evolution of IGN neutral hydrogen fraction is evolving very fast in this redshift range. Now let me briefly summarize our work. So we derive new model-independent upper limits on the IgM neutral hydrogen fraction from 53 high-ratio quasar based on the dark pixels in the lemma alpha and lemma beta forest. And our result comes to the upper limit on neutral hydrogen fraction about 80% at ratio 6.3 and also 80% at ratio 6.5. This upper limit on neutral hydrogen fraction increased to about 95% at ratio 6.7. This very fast increase in the dark pixel fraction might imply a fast evolution in IgM neutral hydrogen fraction in this fraction range. Let me end it here, and thank you very much for listening. I'm happy to take any questions.
Thank you very much for a nice talk. We'll wait 20 seconds or so, and then Steve will ask the first question.
All right, very nice talk, Xiangyu. The first question is, how can you constrain the mean neutral hydrogen fraction from the dark pixel fraction? Doesn't it require you to assume the density PDF?
So let me go back to that slides. So the basic idea is that for the highly ionized region, there are bright pixels. So you just take the opposite of this highly ionized region and use the dark pixel to put upper limit on neutral hydrogen fraction. And so I have a backup slide for this. So for this dark pixel, also it's intrinsic is resolved by neutral hydrogen fraction. Neutral hydrogen is just intrinsically have zero flux, right? So, but there might be sub-2 scenario corresponding to this dark pixels in the observed spectra, but they're associated with quite different neutral hydrogen fraction. So for when we observe a dark pixel, we don't know whether that's 100% neutral or something else. So we can only use this to put up limit on hydrogen. I hope this answers your question.
Okay, so next question is, in McGreer 2015, they used negative pixels to estimate the dark fraction. Have you checked whether that makes a difference to your limits?
So we tried this a little bit, but because our study has some just when we use this 2 sigma noise level, the dark pixel fraction is already pretty close to 1. So it means that when we use the definition of dark pixel, when we count the number of pixels with negative fluxes, we might have just more than 50% pixels with negative fluxes. So if we double that fraction, you will give a fraction more than 1. So I don't think it's very physical for that. And also because for the sky is very noisy at high ratio n, so sometimes the background subtraction is just a little bit over subtracted. So we have some slightly negative offsets in the flux. So that will cause some problems when we use that definition for the high ratio n.
There are a couple questions about the bin size or the pixel size. Could you define what you mean by pixel, and how do you motivate that definition, and how do the results change depending on the pixel size?
Okay, so in our study, we only set this pixel size. So this is about 3.3 microparsec in co-moving distance. So because this, we use this pixel size for all the satellites, and we don't quite test how this pixel size will change our result. I guess probably that's the next step. And the reason why we want to choose a larger pixel size because the limiting object depth is higher for a larger pixel size.
Okay, thank you very much for a nice talk again. You have a couple other questions, so please respond at your convenience in Slack. We'll move on now. Next is Yongda Zhu, and his talk is titled "Chasing the Tail of Reionization Using Dark Gap Statistics in Lyman Alpha Forest."
Okay, can you see my slide?
Yes.
Okay, hello everyone. My name is Yongda Zhu. I'm a third-year PhD student at UC Riverside. I'm very honored to have this opportunity to introduce our new observations near the end of reionization using dark gap statistics. This work is done with Professor Judge Becker and the XQR30 collaboration. So I will start with a brief introduction of our scientific case, our method, and finally the results and discussion. So the scatter in lambda alpha opacity measurements below redshift 6 and the observed long trough towards J0148 extending down to around redshift 5.5 have indicated that reionization may end later than previously believed by redshift 6. And more evidence for an ultralate reionization also comes from the significant evolution of metal absorbers from redshift 6 to 5. For example, this is the O1 absorber. And most importantly, as Chris just mentioned in his talk, the recent measurements on the mean free path of ionizing photons also favors a late reionization. In addition, semi-analytic modeling of variety observations also prefer a late reionization. Therefore, we are interested in whether reionization continued much below redshift 6 and how this can be distinguished from different models based on the lambda alpha forest. So to answer this question, firstly, we want to find out whether there are neutral patches in the IGM below redshift 6 or are there any signatures of this neutral IGM? So we need to quantify the redshift evolution of the lambda alpha opaque regions. One way to do this is identifying individual dark gaps in the lambda alpha forest, which might be caused by the neutral IGM patches. And dark gaps are pretty useful here because they can provide complementary information to the opacity measurement. The tau effective measurements are usually done over large windows, for example, 50 megaparsec over H. The size is shown in this orange box, while dark gaps can provide multi-scale information of the IGM. In this work, we define a dark gap to be continuous regions of a spectrum in which all pixels spin to 1 megaparsec over H have an observed normalized flux less than 5%. And our sample include 56 high-quality spectra of quasars at redshift from 5.5 to 6.5, including 23 new spectra from the XQR30 program. The XQR30 is a VLT large program targeting 30 bright quasars at redshift higher than 5.6. And Valentina will give us a talk on XQR30 program in section 3A tomorrow, so please look forward to it. And finally, by the way, as shown in the blue line, we use PCA to fit the intrinsic continuum of quasar, so which is less biased than the conventional part of fitting. And this figure shows all dark gaps detected with length and their central redshift. The red dots are dark pixels containing metal absorbers, but in total, we detected 49 troughs longer than 30 megaparsec over H, and we display the most interesting ones on the right. So just to draw your attention, firstly, we detected two long dark gaps completely below redshift 5.5 and extending down to 5.3. Both satellites are from the XQR30 program. Then still below redshift 6, in addition to the famous J0148 satellite, we got another two long dark gaps. And here in the bottom, we also display one extremely long trough that has a length of 160 megaparsec. Please note that most small peaks inside each dark gaps are scarce subtraction residues, as are indicated by the flux error rate colored in red. And this figure shows an overview of of our results. Blue shaded regions are the lemma alpha forest, and the black bars indicate dark gaps longer than 30 megaparsec over H. And this figure shows how lemma alpha opaque regions evolve with redshift in an intuitive way. You can see the two long dark gaps below redshift 5.5. And as the redshift increases, there are more and longer troughs. But in order to quantify the evolution of dark gaps, we need to use statistics. The first one is the distribution of dark gap length. And we also introduce a new statistic, F30, which is defined as the fraction of quasar satellites passing through dark gaps longer than 30 megaparsec over H as a function of redshift. So you can imagine a vertical line sweeping along this figure. Here we use 30 because we found that in later reionization models, dark gaps longer than 30 megaparsec over H are likely to contain neutral hydrogen. This figure shows the evolution of cumulative distribution of dark gap length over redshift 5 to 6. You can see a strong evolution below redshift 6. And then this figure shows our main result, the F30. We can see that at redshift 6, about 90% quasar satellites are passing through long gaps. And this fraction becomes 60% at redshift 5.8 and still 15% at 5.6. And the last long dark gap, the long dark gaps persisting down to redshift 5.3. So a good reionization model need to be able to reproduce this result. So in this work, we compare 3 different models, including the baseline homogeneous UV background model and several later reionization models, and finally a fluctuating UV background model, wherein reionization ends by redshift 6, but containing large-scale fluctuating UV background. Here is the comparison between the models and our dark gap measurements. The black curve in each panel shows F30 from the observation, and color shaded regions represent 68 and 95% limits of model predictions. As just mentioned, F30 increases with redshift. The non-zero F30 caused by low redshift dark gaps may suggest that the signature of reionization continues all the way down to redshift around 5.3. Then let's look at the first panel. It compares F30 from the data to the prediction of the homogeneous UV background model. It's evident that fully ionized IgM with a homogeneous UV background is disfavored even down to redshift around 5.3. And then let's look at later reionization models, wherein reionization ends around redshift 5.2 or 5.3. They are all consistent with the observation, except for this one. Oh, sorry. It's in the green box. It's a gradual reionization model with a high midpoint. It's less favored by the observation, and this result is also consistent with the CMB measurements. The rest one color in purple is a fluctuating UV background model. The low UVB regions can also produce long dark gaps. So overall, obviously, both later reionization models and the fluctuating UV background model are consistent with the data, at least over the available redshift range of simulations. The further constraints on these models may come from simulations over a larger redshift range and or different types of observations. As for our next steps, we are working on distinguishing these models using dark gaps in the lemma beta forest, which can be used to trace more opaque regions, and perhaps they include more information. Another robust constraint, of course, will come from the mean free path measurement between redshift 5 to 6, which will give us a better understanding of the IgM evolution near the end of reionization. That's it. Thanks for your attention, and any question?
Thank you, Yongda, for a very nice talk. We'll wait 20 seconds.
Thank you.
All right, so that's the first question. How significant is the line of sight effect in your statistical analysis, following through long filamentary structure versus cutting through the filamentary structure?
This is a great question. So in this work, because we use a large sample, so we assume this effect is not so significant, but we do generate the mock data set to match all of our observation line of sight. So as you can see in the simulation results, they are based on 10,000 realizations with 56 mock data set for each model. So yeah, this is how we handle this effect, but it should be interesting to see the environment of this line of sight in the future.
Okay, the next question is a two-part question. The first one is, any physical reason for choosing 30 megaparsecs as the threshold? And the second part is, the second part is, in comparison with simulation, did you consider the noise levels of the individual quasar spectra?
Thanks. This is a great question. So as you can see in this slide, I calculated the dark gap distribution with and without neutral islands inside. As you can see in the later reionization models, which including the residual neutral islands, you can see starting from like 25 or 30 megaparsec over H, the distribution is dominated with the dark gaps with neutral islands inside. So that's why we use the 30 megaparsec over H as a threshold. As for the second one, for each quasar line of sight, we generate a set of mock spectra, and we tried to match the pixel size and noise level.
Okay, I'll ask the next question. If the long troughs at redshift 5.3 were actually damp Lyman alpha systems, how metal free would they have to be to have avoided detection as metal line absorbers?
So well, well, this is a great question, and I haven't thought about how metal free they should be, but at least in our work, we inspect all of the infrared spectra to search for potential metal absorbers, but we found that even with the strongest DLAs, they cannot create 30 megaparsec over H dark gap by themselves. So I think even they contain metal absorbers, it still will not be a very huge problem for this project.
Okay, so you have a number of other questions in Slack. Please address those when you get a chance. We'll move on. Next is Victoria Straight, and she'll be telling us what we can learn about galaxies and cosmic dawn before JWST.
All right. Yeah, thank you guys for having me. I'm Victoria, and I'm a grad student at UC Davis, working with Marusha Brodach as my main advisor, but I've also had other important mentors, including Brian Lameau, Dan Coe, Deborah Policia, and several others. And I'm going to be moving actually in a few months to the Cosmic Dawn Center in Copenhagen. So I feel a little bit kind of in a gray area right now, but I'm going to be telling you about galaxies at cosmic dawn using Hubble and Spitzer mainly, and a little bit with Keck at the end. There we go. So I know that we're all here because we are interested in cosmic dawn, and maybe we're already interested in galaxies at cosmic dawn. But my personal reasons for why they're interesting are listed here. So first, they're progenitors of all galaxies that we see today, including the Milky Way. They're hosts to the universe's first stars. They're likely responsible mainly for the reionization of neutral hydrogen in the IgM. And I think my favorite reason right now is that they likely have extreme stellar populations, which makes them laboratories for sort of, new mechanisms of star formation or things like that. And so with observations that we've heard about, this morning and yesterday, we can constrain a lot of things on top of just basic stellar populations, including ionization and ionizing bubble sizes, kinematics of gas in the galaxies, and even the first star formation, possibly POP3 components. And so I'm interested in, getting a better handle on all of these things that I have listed here: metallicity, size, age, dust, etc., on top of stellar mass, star formation rate. And I'm taking the approach of using lensing. So I've worked with a few different lensing campaigns, but the one I've worked with the most is the Reionization Lensing Cluster Survey. And this is a survey of 41 massive galaxy clusters that were chosen. I'm plotting here the Planck mass and redshift. They were chosen to just be sort of high redshift and very massive, so that there are lots of high redshift galaxy candidates behind them. Dan Coe PI'd 188 HST Treasury program for these, and my advisor Marusha PI'd a very large, over 1,000-hour Spitzer program. And so there's lots of science being done in relics that I won't talk about, like lensing, supernovae, and galaxy cluster scaling relations. I'll mostly focus on the high redshift because that's what I do, and it's the main goal of the survey. So here I'm plotting the high redshift sample. So there were 21 Hubble selected high redshift candidates. So I'm showing magnitude here in redshift, and the relics candidates are plotted in pink on top of some other high redshift galaxy surveys. And these are just Lyman break selected photometry only candidates. And there are a few spectroscopic follow-up programs on these galaxies. Our group at Davis has been using Keck, Mossfire, Elris, and Deimos to look at a few of the clusters in relics. And there's also folks using Muse and ALMA to follow these up. And like I said, I'll present a Keck result at the end, but I mostly have spent time working on Spitzer observations, imaging from IRAC, just because this is important for doing SEB fitting. So this is just a random example galaxy from a Hubble Frontier Fields cluster, AVAL 370. I'm plotting magnitude versus wavelength here, and then the black points are the data, the photometry from Hubble, and then the blue line here is a best fit BCO3 template. And the point of this slide is just to show you why Spitzer is important. So Spitzer at redshift 6, the rest frame optical falls into the near infrared where Spitzer probes. And so over here, I'm showing the distributions of stellar mass, star formation rate, age, and specific star formation rate with only the Hubble fluxes of this galaxy. And then when we add Spitzer, we can constrain, the light from old stars and emission lines and get a much better handle on these galaxy properties. Oops. And so there were 300 galaxies in the sample, and these are the 3 that I've kind of chosen to highlight and tell you about. The first sort of exciting thing to come out of the sample was this spatially resolved redshift 10 arc. This is exciting because anything extended at high redshift is exciting. You can even see separate clumps in this. And unfortunately, it was very blended with a bright neighboring galaxy in Spitzer. So we could only get upper limits in flux, but it was enough to securely put the redshift at redshift 10. So this is, we hope to follow this up and learn more about it, but it is securely a lensed redshift 10 galaxy. The one in the middle here was a redshift 8.4 galaxy discovered behind Abell 1763. And the interesting thing about this galaxy is that it shows evidence of a Balmer break, which means that there are old stars in the galaxy. It's evolved, meaning, it's been around for around a couple 100 million years, which is significant at redshift 8 because the universe is only a few 100 million years old. And that means that the stars in this galaxy must have started forming very early. So this is sort of an indirect way to put a constraint on the first star formation. And then the last galaxy over here is one behind Planck 287, and it's showing an elevated channel 1 Spitzer flux, which we believe, like many others have seen, points to extreme O3 H beta emission, at least 1,000 angstroms in equivalent width. And this galaxy is at redshift 6.8. So we're, of course, not the only ones to have. Lots of other people are seeing this sort of galaxy popping up in our sample too. And these 2 galaxies are just sort of examples of lots of other similar ones that we found. So we found several other Balmer break galaxies and several other extreme O3H beta emission galaxies. And so since I don't have time to tell you about all 300 galaxies, these are some diagnostic plots of luminosity, stellar mass, and age. I was able to release a public catalog of all the data for 2/3 of the galaxies that I could extract Spitzer fluxes from. And so that's available at my website if you're interested. It has Hubble and Spitzer fluxes and stellar population fits with lots of different parameters from 2 very different SED fitting methods. See. And so one other interesting result to come out of this this survey was some work done by an undergrad at UC Davis, Chloe Neufeld. She's been using a code called linstruction to de-lens all of the high redshift relic sources and then measure their sizes. And so here we're plotting half-light radius in kiloparsecs versus magnitude, comparing to some redshift 1 to 3 sources in purple here, and then to Richard Bowen's 2017 size results here in the triangles. And our results are in stars. And so you can see that compared to Bowen's Hubble Frontier Fields results, ours are brighter, but we are finding quite small galaxies. And so this project is with the main goal of looking for highly star-forming compact galaxies that could likely be Lyman continuum leakers. And I have to put in a plug for Chloe. She's applying to grad school this year in the US and in Europe. And she's an excellent student, so look out for her application. And so the last result from relics that I'll talk about is this galaxy, the dichromatic primeval galaxy at redshift 7. This thing we detected in Lyman alpha with LRIS on Keck, and saw that it had a huge Lyman alpha equivalent width of 200 angstroms, and it was spatially resolved. And so this is kind of at odds with the SED here, which shows very red beta slope and bright IRAC fluxes. And it's also quite faint. It's 0.3 L star. And so this galaxy was puzzling to us. And it also made us think of, these other named galaxies on this plot, CR7, Masosa, Cola 1. And so you can see on this Lyman alpha equivalent width versus UV luminosity, DP7 is the strongest, or one of the strongest Lyman alpha emitters, one of the faintest and one of the reddest. So this is the reddest. It's colored by UV beta slope. And so compared to some of these other named galaxies, we think it's similar. Maybe it's carved out its own ionized bubble, or it's a fainter galaxy within one, possibly could have POP3 or metal core component. And several of these other galaxies also point to possible evidence of a merger or accretion event. And so upon a little bit of a closer look at our HST data, we saw that DP7 does in fact have two distinct components in the UV, and with almost significantly different beta slopes. So it seems that this could possibly be evidence for a merger and accretion event as well. And so we have an HST proposal in to nail these beta slopes down a little bit, and we have an ALMA proposal in to look at the C2 in the galaxy to study the ISM. And we have a denied James Webb proposal that I won't give up on. So I think I'll just leave my slide up here and take questions.
Thank you, Victoria, for a nice talk. We'll wait 20 seconds.
Thanks, Victoria. So I'll ask your first question, which is, how do you model dust attenuation in your SED fitting?
Yeah, so we do SED fitting with two different methods. They're very different, and I can go into more detail than I showed right now. But so with the first method, we use easy to constrain redshift, and then we use BCO3 templates, which just assume some kind of dust law. And I think we chose SMC for that one. And I think for the other one, we use bagpipes to model to do SED fitting for a second method, and we assume dust around the birth cloud and a Calzetti dust law.
Okay, next question is, what is your favorite star formation rate history in your SED fitting?
Sorry, I think I broke up here a little bit. Did you say what is my favorite star formation history?
Yes, in your SED fitting.
Okay. So I think my favorite one right now is we're just using a variable star formation history that allows increasing, decreasing, and constant, just for the freedom of it. But at high redshift, it ends up not mattering that much because there isn't much time.
So how do you account for blending with the cluster galaxies, and how much of an issue is crowding in the cluster cores and the IRAC imaging?
Yeah, so I use a code called TFOT to account for blending, which uses like a template-based approach to model each galaxy in the field, and it uses Hubble as a prior, and then it degrades that resolution to Spitzer resolution, and then we can kind of fit for the Spitzer fluxes, although it's not perfect. So I think that in one of my slides, I said, we only have 200 of the 300 galaxies Spitzer fluxes, and that's because 100 of them were, too severely blended by cluster members. So cluster fields, this is hard to do in cluster fields, so we can't always get Spitzer fluxes.
Okay, so you have a couple more questions in Slack to address when you get a chance. Thank you very much again for a nice talk, and we're going to move on now to Holly Christensen, constraining the end of ionization with the opacity density relation at redshift less than 6.
Okay. Thank you for that introduction. Oops. Oh, I'm on the wrong slide here. That's embarrassing. All right, thank you for that introduction. I wanted to get started by placing my work in a broader context, namely that there's a growing number of observations that point to a late and fast reionization. So just a quick overview. Some of those are the cosmic microwave background constraints, which place a midpoint of reionization at redshift of about 7.7. The drop off in the fraction of galaxies that emit Lyman alpha, it ratios greater than 6, which gives us a constraint on the neutral fraction, that and the dark pixel constraints we were hearing about earlier. The mean free path measurement of redshift 6, which we've also heard about in this session, and a number of observations from quasar sightlines, including the presence of damping wings at redshift 7, which indicates some presence of neutral hydrogen. All of those observations together paint a picture of a reionization that happens mostly between redshift 6 and 8. There is one observation from quasar sightlines that particularly motivates my work. That is the observed scatter in the effective Lyman alpha opacity at redshifts greater than about 5.5. So here we have a collection of effective opacity measurements from the literature, plotted as a function of redshift. And we can see that the scatter is pretty tight at the lower end of this redshift range, whereas we get to higher redshifts, we start seeing more and more scatter. And in particular, there's some really highly opaque sightlines at redshifts of about 5.7, which correspond to large Lyman alpha troughs in the spectra of those quasars. And it's not simple to explain why we should be seeing this scattered Lyman alpha opacity. So the questions that motivate my work are, what causes the observed scatter in Lyman alpha opacity? And what does the answer to that question tell us about reionization and how it ends? So there are 3 models that have emerged that attempt to reproduce and explain the scatter in Lyman alpha opacity. So I'm focusing on those 3 types of models. The first is the temperature model, which attributes the scatter to large-scale fluctuations in the IGM temperature. In the temperature model, a highly opaque sightline corresponds to an overdense region, which reionized earlier and has been cooling for longer, making it more highly opaque. The second model is based on large-scale fluctuations in the ultraviolet background. So in the UVB model, a highly opaque sightline corresponds to an underdense region, which is associated with a suppressed ionizing background. And the third possibility is this ultralate reionization scenario, which we've heard about from a couple other speakers in this session, in which reionization is still ongoing at redshift 5.7 or so and lower. And in this scenario, a highly opaque sightline corresponds to a region of a neutral island of hydrogen that has not yet been reionized. So each of these models makes a robust prediction for what we expect to see in terms of density associated with the highly opaque sightline. And I've just included this figure as an example. This is from the UVB model. The grayscale color bar indicates the effective opacity, and the colored points indicate the positions of Lyman alpha emitters in the simulation. They're color-coded by their narrowband magnitude. These blue and red circles indicate regions of particularly high and low opacity, respectively. And those illustrate the prediction for density that I've described here is that this blue region, this blue circle picks out a marked underdensity of Lyman alpha emitters, whereas the opposite is true for a transmissive region. So given that these 3 models make opposite, sometimes opposite, sometimes not, predictions for the relationship between density and opacity, I want to test them out observationally. And the way that we do that is by characterizing the density associated with these highly opaque and highly transmissive sightlines. So I do that by using Subaru Hypersupreme Cam to select Lyman alpha emitters in fields surrounding particularly extreme quasar sightlines. So our program includes 4 quasar sightlines, 2 highly transmissive sightlines, which you can see here are the top 2, and 2 highly opaque sightlines, the lower 2. And you can see in those 2 highly opaque sightlines, there's a very clear Lyman alpha trough. I've also overplotted the transmission filter curve for the narrowband filter that we use to select Lyman alpha emitters in these fields. That corresponds well with the Lyman alpha troughs that we see in the lower 2 spectra. And that's one reason that we opted to use Hypersupreme Cam is that it has a narrowband filter well tuned to selecting Lyman alpha emitters at redshift 5.7. Just as a note, one of the highly opaque sightlines in our program, J148, was previously published as a pilot study for this program by Becker et al. 2018, and has also been followed up by Kishino et al. 2020, so I recommend checking out those papers. The first phase of this program is surveying the 2 highly opaque sightlines, and we've recently submitted those observations to AppJ. So I wanted to share with you the results from those 2 surveys. So these 2 figures show the LAE maps that were selected in these 2 fields, J148 on the left and J1250 on the right. The colored points indicate the positions of Lyman alpha emitters that we select. They're color-coded by their narrow band magnitude. And the grayscale color bar in the background indicates the surface density of Lyman alpha emitters. These 2 fields are centered on the quasar sightline, which is marked with a gold star, and the concentric circles just indicate increments of 10 megaparsecs. There are, just as if you're familiar with the J148 result that's been previously published, this is just a slightly updated version. We've improved our photometry and LAE selection criteria a tad, but fundamentally the result has not changed at all. We still see a clear underdensity of Lyman alpha emitters in the center of this field. And in the J1250 field, there's also a clear underdensity of Lyman alpha emitters in the center of the field. The other reason we opted to use HyperSupremeCam is that we get a really large field of view. And so when we're characterizing the density, we're really interested in characterizing the density in the vicinity of the quasar sightline within 10 or 20 megaparsecs and comparing that to the larger field to get an idea of whether it's over or under dense relative to its surroundings. So these are the 2 clear underdensities that we're looking at. So these 2 fields provide a nice clear result that we can and do compare to predictions from different models. So these figures show the surface density of Lyman alpha emitters in each of these 2 fields as a function of distance from the quasar sightline. And they are normalized to the mean surface density in the field. And in each of these 6 panels, they're compared to predictions from a different model. So for each of these models, the dark line indicates the mean model prediction, and the shaded region indicates the range of expected values. So there are 6 models here. I would like to start by drawing your attention to the 2 on the left, the upper and lower left. These 2 models are variations on the ultraviolet background model, which made a clear prediction that a highly opaque sightline should be underdense, and that agrees well with our results in these 2 fields. Here in the upper right, we have the temperature model, which predicted that a highly opaque sightline should be an overdensity. That is the opposite of what we're observing in these 2 fields, and our observations disfavor this model. In the lower center and right, these are 2 variations on a late reionization model, which made a clear prediction for highly opaque sightlines that they should be underdense, and that agrees well with our observations. So phase 1 of this project has clear results that we are disfavoring the temperature model and confirming these results from a pilot study in a second highly opaque sightline. If we want to take this further and try to understand which, if either, of the UVB and late reionization models are preferred by the observations, we need to move on to phase 2 of this project, which considers highly transmissive sightlines. We have recently been able to select LEUs in a highly transmissive sightline. So I will show you that, but first I want to comment quickly on the model predictions for the highly transmissive case. The UVB model makes a clear prediction that a highly transmissive sightline should correspond to an overdensity of Lyman alpha emitters. The late reionization case is slightly less clear. It makes a robust prediction for the highly opaque case, but Mr. and Deloisio find that a transmissive sightline could arise from a range of possible densities, so there isn't quite that clear-cut transmissive, definitely one or the other. So there's a range of possibilities there. So keeping those model predictions in mind, here are the LAEs that we select in this J1306 field, which is our first look at a transmissive sightline. This uses the same format as before, where it's a map of our LAE candidates. And there are 2 things that are striking about this figure. The first is that there is a pretty clear underdensity in the center part of this field within 10 or 20 megaparsecs of the quasar sightline. And the second is this large overdensity that is directly adjacent to the center of the field. So this is a pretty preliminary result. It's not immediately clear yet if or how important that large overdensity is, but it's certainly intriguing. Taken at face value, these results disfavor the UVB model, which predicted that we should be seeing an overdensity in the center of this field. But it's consistent with predictions from the late reionization model, which allowed for a broader range of possible densities. Like I said, it's not entirely clear yet, how to interpret this, but one possible interpretation that is interesting is that this highly transmissive sightline is showing us a region that has been recently reionized, potentially by all of the ionizing sources that are present in this large overdensity. So with that, just to conclude, we've confirmed the association between highly opaque sightlines and underdensities in 2 fields now. And our first observation of the transmissive sightline are pretty interesting. They show an underdensity that at face value disfavors the UVB model, and it's consistent with predictions from the late reionization model. So I'll leave you there.
Thank you, Holly. Very nice talk. We'll wait a little bit for questions.
All right, so that's the first question. How do you distinguish between a real deficit of galaxies and a bunch of galaxies which have not been able to ionize their surroundings yet?
That's a great question. I mean, I think an interesting or an important thing to mention is the other authors that have looked at this sightline, because you know what, all 2020 were interested in kind of the same question. So they looked for continuum selected galaxies, and they've published a selection of continuum selected galaxies in this field, which we wouldn't expect to be suppressed by neutral hydrogen. So the J148 field, they're able to reproduce the deficit of galaxies we find in the J148 field, and we actually have some additional data from Subaru to make that selection ourselves, and our preliminary results are consistent with the same thing. We also reproduce our underdensity of galaxies, so that's been an important kind of check in our work to verify that the void we're seeing is real.
While we're waiting for other question, okay, another question came in. Said I may have missed, but why is the UVB model disfavored?
So the UVB model predicted that a highly transmissive sightline should correspond to an overdensity, so it's nearby a lot of ionizing sources, and that is not what we're seeing here in the J1306 field. So this prediction is specifically for really close to the quasar sightline. I guess I can show you the predictions here. So this is for the highly opaque models, but just to give you an idea of what these predictions look like, you expect to see, we're interested in like a differential measurement where we're comparing the very inner part of the field to the rest of the field. So that inner 10 to 20 megaparsecs is really where we're making this comparison. So for example, in the highly opaque sightlines, we see these models predict a deficit of LEUs in the inner part of the field, and then it comes back up to the average. So coming back to this result in the J1306 field, we see this pretty clear deficit in the very central part of the field. And at least at face value, that's not consistent with what the UVB model predicts, which is that we should be seeing an overdensity in this part of the field.
Okay, so another question about the UVB models. So in those models, what is the variance between overdensity and opacity? For example, if the UVB model was right, how unlikely is it to find an ionized region that is not overdense?
That is a great question. I'm not sure that I don't happen to have detailed predictions from the UVB model to hand right now. This is a pretty preliminary, this result's pretty preliminary, but that is a great question, and I will definitely jot that down to follow up on.
Okay, looks like you have a couple other comments in the Slack, but thank you very much again, Holly. In the interest of time, we'll move on. And so our last talk of this session is Hyunbae Park, crucial factors of Lyman alpha transmission in the reionizing intergalactic medium.
Hi, you hear my voice and see my screen?
Yes, we do. Thank you.
Okay, thank you. I'm Hyunbaek Park from Kavli IPMU. First of all, I'd like to really thank the organizers for this great conference and the opportunity to present. So this talk is about IgM transmissivity of Lyman alpha photons during reionization based on the CODA2 simulation data. So just for a brief introduction, Lyman alpha emission from high redshift galaxies is considered as a promising probable reionization history because Lyman alpha photons are easily scattered off the line of sight by neutral hydrogen gas in the intergalactic medium. So recent observations do find that the chance of finding LAEs decrease steeply above redshift 6, especially for relative faint galaxies. There are some preliminary constraints on the IgM neutral fraction based on these observations, although they have not converged yet. So when future experiments like JWST launches, we expect to have a huge development on these subjects. So the motivation of this work is to try calculating the Lyman alpha transmissivity in a simulated IgM to quantitatively understand how the IgM during reionization affects the observability of LAEs. In this regard, the CODA2 simulation provides high resolution data of IgM during reionization in a fairly large volume. In the simulation, the cold dense gas is converted into stars with some prescriptions, and the ionization by these stars is computed simultaneously with its feedback on the IgM to produce density, velocity, and temperature field that we need for calculating the Lyman alpha opacity. So you can find the details of these great simulations from the Osberg et al. 2020. So here are H1 density maps at different scales for a galaxy at redshift 7. Blue is neutral, red is ionized. So I assume the IgM around the galaxy is defined as the gas outside the video radius and calculate the optical depth by integrating the cross-section times H1 number density outward from there. So the Lyman alpha cross-section is largest at the line center, of course, and then it also has a damping tail extended outward. So every photon emitted on the blue side of the line center will be scattered eventually because they will redshift into the line center at some point where the cross-section is very large. But then also a fraction of photons emitted on the red side will be scattered too in the neutral IgM because of this damping mean opacity. And this damping mean opacity depends sensitively on the H2 region size because the more photon redshift away from the line center in the H2 region, the lower the damping ring cross-section is. So we look at the transmission curve for this particular line of sight shown as the green arrow in the lower center panel. And the transmission curve has typically has a shape of a step function where the transmission is 0 below certain wavelengths and non-zero but below 1 above certain wavelengths due to the damping mean opacity. So interestingly, the line center absorption extends to the red side of the line center because the IgM around the galaxy typically gravitationally enforce toward the center. Blue shifting the photons in the rest frame of the IgM. So the location of this transmission cutoff indicates the maximum IgM impulse velocity around the source galaxy. So in the lower right panel, I create the model double peak profile for the intrinsic emission coming from the galaxy and multiply that to the transmission to obtain the observed line profile shown as the solid line. Typically, the blue emission is completely suppressed and some part of red peak is also truncated by this involving IgM. So here, here are the transmission curves for different sight lines for 3 galaxies with different halo masses at redshift 7. If you focus on the location of the cutoff, you see that the offset between the cutoff and the line center are larger for more massive galaxies. So this is because more massive galaxies have stronger gravity, leading to stronger effect motion. In the lower left is the probability density distribution of the simple velocity, which shows basically the same trend. And the lower center part shows the impulse velocity as a function of halo mass. And here the error bars on each data point is the 1 sigma range obtained from 2000 sight lines for each galaxy. So we find that basically the simple velocity is very similar to the circular velocity of the post dark matter halo with some scatter. And the UV magnitude also has a similar relation with the impulse velocity because it correlates with halo mass. I move on to the damping mean opacity on the red side of the cutoff. The neutral density maps around the same galaxy redshift 6, 7, and 8 shows the increasing neutral fraction in the IgM toward high Z. So the transmission curves at the bottom show that the red side transmission decreases toward the high redshift. So the evolution in the transmission is obviously coming from the ionized regions becoming smaller toward higher redshift. The median distance from the galaxy to the bubble edge, the RB, is larger for galaxies at redshift 7 than that at redshift of 8. And the dotted curve here in the right panels are the corresponding transmission curves for those median H2 bubble sizes. And also we compare bright and faint galaxies to understand why LAEs are more difficult to find in faint galaxies at high redshift. So in the H2 density maps here on these two groups, the difference is not as clear as in the redshift dependence, but if you see carefully, faint galaxies are more likely to reside in small H2 regions than the brighter ones do, presumably because they emit less ionizing photons. So these maps tell us how complex and diverse the H2 region shape can be in reality. If you compare the median transmission curves in the right panel, see there are two differences. So first, the transmission cutoff appears at a shorter wavelength for fainter galaxies because they're less massive on average and the inflow motion is weaker. And also the transmission on the red side of the cutoff is lower for the fainter galaxies because the H2 bubble sizes are smaller for them. So here we multiply the transmissivity to the model emission profiles. We give a broader line profile to brighter galaxies because they're expected to require a larger frequency offset for the photons to escape the galaxy. So these results have a number of interesting aspects. So first of all, some part of emission is still scattered by the infalling IgM, even at redshift 6, where the IgM is almost fully ionized. And then the transmission of the red side of the cutoff decreases toward high redshift. And you can see that brighter galaxies are relatively less suppressed than the fainter ones do, which is consistent with the observation. And there are two reasons for this. One is the difference in the bubble size. Brighter galaxies are in larger H2 bubbles on average. And the other is that the brighter galaxies transmit redder photons because of the stronger inflow motion and larger offset in the intrinsic profile. So basically, the redder photons are subject to less opacity for given bubble size. And I find that these two factors are comparably important in the UV magnitude dependence. Now I would like to list some interesting cases I found in the analysis. So in this example, I'm showing two sight lines shown as dotted lines here that are only 3 degrees apart, but the transmission is almost 4 times lower for one of the sight line. And what's happening here is that one of the sight line goes right through a dense self-shielded neutral gas system inside the H2 region, shown as this blue region in the map, where the transmission is highly suppressed. And we expect to have a lot of such self-shielded systems during reionization. So this case demonstrates how Lyman-alpha emission can be suppressed even in highly ionized regions. This is another interesting case. So this sight line, this faint dotted line, goes right through an extremely low H1 density blob, shown as dark red in this map. This blob was created by supernova explosions in the neighboring galaxy, and H1 density here is so low that photons can be transmitted even when they're at the line center in the rest frame of the IgM. As a result, some photons leak through this window, creating a double peak like feature in the spectrum. But this is pseudo double peak because both peaks actually come from the same red peak in the intrinsic profile. So there are currently a few double peak LAEs observed around redshift 6, which call for explanation. I think this case makes an interesting potential scenario for them. So here are the full statistics of Lyman-alpha transmission as a function of UV magnitude from CODA2. And by taking the ratio of redshift 7 and 8 result, this black lines for the median, to the redshift 6 result, we obtained the relative suppression by the neutral IgM shown in this table. And you can basically see the redshift and UV magnitude dependencies, which I already discussed. And I'd like to lastly briefly talk about the variance in this relation shown as the gray shade. So the variation in the transmission comes from the complexity of H2 bubble shape, making it difficult to constrain the average transmission with a small number of observations. So if we take the ratio of the 1 sigma range to the median value, it is greater than 1 for most galaxies at redshift 7 and above, which means that we need more than 100 galaxies to suppress this variation to 10% level. And the current constraints are at above Redshift 7 are based on less than 100 galaxies. So I think this may be why the constraints have not converged yet. But of course, future experiments like JWST and NGRST and Euclid will improve on this by enlarging the sample size. And according to our results, brighter galaxies have relatively smaller variation in the transmission. So in that sense, maybe NGRST and Euclid might be more efficient because they're more focused on brighter galaxies in the wider fields compared to JWST. Yeah, so I quickly listed my findings from the CODA2 simulation. I'll leave the summary slide on and take questions. Thanks for listening.
Thank you, Hyunbae. Very nice talk.
Yeah.
Hi, Hyunbae. Very nice talk. So I'll ask first question. What is the Lyman alpha escape fraction below the resolution of the simulation?
I don't think the simulation assumes any Lyman alpha escape. Actually, the simulation does not simulate Lyman alpha photons. It only simulates the ionizing photons, and there's an escape fraction for the ionizing photons. And I basically calculate the Lyman alpha transmission using the ionization field and density field produced by the simulation. Not sure I'm answering the question.
I guess a follow-up is, do you have any ISM or CGM absorption or attenuation on the Lyman alpha, or are you assuming all the Lyman alpha that's made in a galaxy gets out and is then susceptible to IGM absorption?
Oh yeah, so yeah, I'm basically assuming CGM and ISM as a black box because it's not well resolved by the simulation. So yeah, as I showed, I'm only assuming a simple double peak profile. Basically assuming that I don't know anything about what's happening in the CGM.
Okay, does your intrinsic Lyman alpha luminosity depend on the escape fraction of ionizing photons?
Could you repeat that? Actually.
Yeah, does your intrinsic Lyman alpha luminosity depend on the escape fraction of ionizing photons?
So Lyman alpha luminosity, we do not assume any Lyman alpha luminosity here. We only assume the shape and try only calculate the ratio between the shape without any normalization and to get the fraction of Lyman alpha photons that escape. So yeah, we will get to that part in our next studies.
Okay, another question has to do with double peak sources, or really sources where you see blue emission. Can you quantify how common or rare those sources like COLA1 should be?
Yeah, so I can talk about this pseudo double peak feature I found from the simulation. And I would say it's rare. And I kind of found this by eyes going through different transmission curves. But it's not impossibly rare. Like I find it maybe 1% of the time from different transmission curves. And I think this is another interesting thing to expand upon using the CODA2 simulation data. I'm going to explore that further.
Is the simulation targeted to produce high overdensities to compare to observations?
So CODA2 has fairly large volume of 64 megaparsec over H. And yeah, it definitely has overdense regions with large H2 bubble. And I know there are observations suggesting on overdensity of galaxies with presumably large H2 region. And I think that's another interesting topic to study with CODA2.
All right, I'll ask one more. Do you need to consider the metallicity of the gas at these high redshifts?
So I think in the IGM, we don't have to, right? So there may be some metals in CGM and ISM, but maybe we can almost assume in the IGM, there is no metal. And that's what I'm calculating here for now.
Okay, I'd like to thank the speakers again for giving some very interesting talks. This concludes session 2B, and we'll see you for session 3. Thank you very much, everybody.
So everybody, just a couple reminders. Session 3A is at a different time. This is at 0800 UTC, followed immediately by session 3B, and then sessions 4A and 4B will be at the regular time. Wednesday has 4 sessions in total. And the Wonder Me will remain open if anybody wants to get together and chat. Otherwise, we will see you tomorrow.